Okay. Any questions about the exam? No? Okay. Any questions about the lecture so far? Today we will finish the radiation problem from spherical sources. I will do some examples. What you have learned so far is wave equation in spherical coordinates, how to separate the variables and have a general solution and then reduce the general solution to specific cases. Now, if we have particular type of examples, how would you solve them? This is what we're going to do today. Do you have any questions? Nothing? Okay, let's start then. Now, what I want to do first is just give you a very general approach, and then we'll go into the more specifics and simplifications and so on. Now, let's say spherical radiation. Now, when we say radiation, that means it's radiating from a source, okay? It emanates, it goes away from a source. So, spherical radiation. And let's look at the case of axisymmetric source. Sources, okay. Now, from the previous approaches, we have already expressed the pressure in a general form for axis symmetry, okay? Now, this of course means symmetric about phi, and that implies n is equal to 0 in our previous expressions. Okay. And the solution is in the form of an infinite series, constant coefficients, Legendre polynomials, and in the case of radiation, Bessel functions of the first kind and harmonic time dependence. Okay. Now, by the end of today, you need to be very familiar with this. You look at this, you say, I know exactly what to do. Okay? The pressure, amplitudes, which are constant. These are Legendre polynomials, Bessel functions. Okay? Now, what's eta? Cosine theta. Correct? Now, cosine theta, let me just remind you one more time. If this is a sphere, for instance, and we say theta is this angle. Okay? What does that mean on a sphere? What that means on a sphere is it defines a circular area because it's a azimuthal, okay? Or polar, sorry, this is a polar angle. So it defines a theta all the way around z-axis. So you have to kind of keep that in mind. All right, and the Bessel functions of the first kind define radiation only, okay? And this one, if you remember, you should, Jm okay, Bessel functions, Newman functions. When this is plus, okay, it describes the radiation component. If it were negative, it would be the inward coming component. Now, what is Am? How do you find it? Exactly, the boundary conditions. In this case, we're talking about an axisymmetric spherical source. So how would you get the boundary condition? Boundary condition. What is a boundary condition? Usually, what is a boundary condition?
The amplitude of the surface?
Yeah, amplitude of vibration. Okay, vibration amplitude. Now, why are we using the vibration amplitude on the surface but not the pressure?
I think we can measure.
Exactly. See, you can measure a lot easier the vibration of a surface than the pressure on the surface. That's the reason. It's just a very practical reason that drives the mathematical modeling for that. So we get the, let me just be more complete. Radial. This is also important that you keep in mind. Now this u, particle velocity, is in the radial direction because there are particle velocities in tangential direction also. Why not? Because air is moving in all different directions. You can get that by doing, in this case, del P over del theta, for example. But we don't measure it, and it's not relevant to what we're doing. Okay, it's only in the radial direction.
Because it's normal?
Normal, exactly. That's pushing the air out. This is not changing the pressure, unless there's heavy viscosity, etc. So that's the part. And when you do that, okay. Finally, okay. You write that down and let me explain something here. When you take a derivative, okay, gradient of pressure with respect to R, okay, this is the only component that depends on R, okay? So what we are really doing is we're saying dHm kr. Make a note of this on the side. This is what we're trying to do. But in order to be able to write this a little differently, then we say, let's multiply it by k and divide it by k. So you have, it's just a little math property, nothing too complicated, dkr. And that gives you hm1 kr prime. Okay, that's a derivative. Then the reason also we do it that way is then this has approximations for large values of kr, small values of kr, and so on. And so what we have done here is do that, and then by multiplying it by k here, you can see it reduces to I over rho c. Okay? Do you follow? Any problems? Okay. So, and one other thing that we do here is just simple reorganization. Okay, just those two terms. I'm going to write it a little bit differently. This equation here, we write it as Bm Kr e to the I. This will become a little bit more obvious. What we're doing here is expressing it in terms of some real number and a complex number. Okay, that's. Let me rewrite this one more time. Oh, this should, sorry. Make sure this is an M here. Function of Kr and some exponential function. This is the complex form, that's the real part. Now, using this, the particle velocity now becomes okay. Now, the velocity on the surface we usually expand it in Legendre functions, the orthogonal functions. You have a radial velocity, right, going in and out, or different shapes, but there's also the angular distribution. Now, the next thing we want to do is look at the angular distribution. So, on the surface means at r equal to a, okay? That's the radius. So, on the surface, how is the velocity distributed in an angular form? Because what you have done is you're measuring the velocity in different parts through various means. Now we are expressing it in a mathematical form. Okay. Okay, so this is a given, and this is the particle velocity from the pressure relationship. So we set these equal to one another, and that's what gives us the coefficients A sub m. put a box around it because this is something we will refer to periodically as we go further and further. One more time, let me just make something clear here. Just heads up just for a second. The velocity expression is this. As you remember, and we will see, we will do some examples. M is determined by this distribution on the source of the velocity. And that, in turn, determines what the coefficients will be, and from which everything just kind of falls into place, and then we have the pressure expression. In fact, if we substitute it back here, the pressure will be okay, this is now the pressure expression for an axisymmetric source that's radiating. So when we see a problem that says here's a spherical source that has axisymmetry, okay, how would you find the pressure? You look at this expression from which you find the coefficients of um by expanding the velocity that's given to you. Okay, now let's okay. Now some basic assumptions or asymptotic relations. What we mean by asymptotic relations is when you're extreme cases, when you're very far away or when the source is very small, what happens? To understand, in almost all mathematical problems, I think we talked about this, but I'm not sure, you look at the extreme cases. If you go to infinity, or if you're at the surface, or if something gets very large, very small, the results should be pretty obvious, and it should make sense. So for this case, first of all, we say far field. How would you define far field? Far field usually is defined as Kr being much larger than Ka. And what that means is R is much larger than A, and also 1. Okay? That again suggests, what does it suggest? Can you kind of think about this? What do they tell you? And how do you know? Take a look at it. Make substitutions in your mind or on a piece of paper. See what exactly, what physically they represent. Because it's important to understand the meaning of these little relationships here. Any ideas? Yes.
Be larger than lambda.
Ah, okay. That's exactly, yes. See, if you make a substitution for this, then you have 2 pi over lambda r is much larger than 1. And that really also says 2 pi r right? For a given wavelength, you're far, far away. And this is essentially the same idea, but in this case, the distance where you're making measurements or you're interested in computing is much larger than the source diameter. That's why it's called far field. Okay? And why is that? Because it allows us also to make some assumptions. So
Can we assume that it's totally harmonic when
that's what we're assuming now. Harmonic in time, right? Yes, that's what we're assuming. We can look at time dependent, but then we solve it all in time and without the use of this harmonic dependence, because sudden expansion, explosions, etc., would be transient sound radiation, and they're slightly different modeling for those. So for far field, then, one of the things we do is, if you look at here, Bessel function is the one that's involved in the far field, right? So we take a look at what values that would take in the far field. Any guesses?
our goes to
It becomes very large, yes. What would, any guesses? Remember radiation in a far field? You'll see in a moment. The expansion the approximate value is okay. You can see it varies. It can be approximated by 1 over kr and an exponential. Now, this is a expression that you can also write in terms of an exponent. Have you ever seen, you may have in your undergraduate classes, how can you express this as an exponential function? Do you know? Never seen it? Okay. Say again?
cosine theta minus b times sin theta.
Something like that, right? Because I is what? If you can do this, this would be equal only if theta is pi over 2, then they're equal. If you want to make this minus, then this would be minus. Okay? And if you want to make this, then you're getting involved. And this expression then would be minus I m, I think 1, yes, pi over 2. M, of course, is 0, 1, 2, and so on. Okay. Now, what we're doing in all of this is make it mathematically simpler to express, so your computations will also be easier to conduct. So the far field expression, pressure, now an approximate, okay, because it's in the far field we're estimating, is we're going to substitute for pressure the approximate value here. the corresponding intensity in the far field again. This would be the intensity expression for the pressure. You see, cross products do not appear because of orthogonalization, okay? Because they're orthogonal. There's no Pm sub S. Intensity is different at different angles. How would you find the sound power of a source? How would you find the sound power? Yeah.
Intensity times area.
Intensity times area. Okay. What else? I mean, what is the area here? Which area would you multiply it with? That's generally true. What area would you multiply it with? If you think about something like this, a spherical source radiating, okay? And what you have here is an intensity expression with coordinates r theta, because phi is symmetric. Which area would you multiply it? You're raising your hand or you're just waving your hand? Emre, do you know? Emrullah knows, but he will tell us later. Okay. What is...
I think in a specific direction theta, the radial area normal. But how can we calculate it?
No, but is that the power? What is a power? Power is the total power that a source radiates. That's how you characterize.
But you said intensity changes with the directions.
Okay.
Power should also change.
Okay. Power should change. Intensity changes, but power should change. With what? Direction? No, but we're having this discussion because I want you to remember these things later. Go ahead.
The angle theta from 0 to 180, I need to calculate area by integration.
You integrate. Okay. What you want to do is when you have an intensity, okay, in all different directions, you calculate all of it at a particular distance. That would be the area. It can be any distance. It doesn't really matter. And that sum gives you the power of the source. That's what it is. Okay. So of course the easiest may be the surface, but it can be any distance that you can integrate it at. So let's see. Let's just write a general expression. The sound power with a capital pi. We use that as the power. First of all, you have to integrate it from 0 to 2 pi for d phi. It's symmetric around phi, but that doesn't mean it doesn't radiate, okay? It radiates in that direction. And then, as Emrullah said, from 0 to pi, we integrate with respect to theta. Now we have an area, square times intensity, sine theta, d theta. And this is the calculation here. Now, just for a moment, if this is 1, what would this be? What would this integration be? What should it be? Say again? 0. Okay, that's 1. Any other? 0. Okay, very good. John? Yes, what?
Yes.
0. All right, you all get zeros. How can it be? Think about it. First of all, if intensity was 1, okay? If this is 0, if intensity is IR, it still is going to be 0. But this is the equation to calculate the area of a sphere, right? If you consider this to be du, u will be cosine theta. So this is cosine theta from 0 to pi, and that's going to give you 2. And d phi is going to give you phi, which is 2 pi. And then you have this, so what does this give you? What's that? What is it? Sorry? Square? Area of the sphere, yes. This is the area of the sphere. That's what it should give. Where'd you get 0 from? From but how could it be 0? Oh, all right. Okay, well, hopefully what these do is help you see the relationships between all these terms, okay? Now, essentially you are covering the variation of intensity around a spherical surface, and that will give you the power expression. So if we take that intensity over here and integrate it, this of course represents in some ways, okay, minus d eta. And the net result of this should be the way, of course, you have to remember what we have done to get to this point is now. I have a disagreement with some of the text information. So let's put a question mark here and see if we can confirm or deny it. I think that has to be a 4 here, but you'll see this in some of the texts. So if you look at here now as sound power, what does it depend on? Depends on these coefficients that represent the surface velocity, okay, the expression for the surface velocity. Similarly, Bm, which we put a, where is the, did we erase it? Yes. Expression, which is a constant, I'll give you some of those values too, and 2m plus 1. Now, if m is equal to 0, what does that mean? If m is equal to 0, it's symmetric with respect to theta. Okay? Now, this is now the general expression. The next thing that we do a couple of different things, and you'll see this in some of the books that you do study from. This expression, for instance, has a dependence on r, dependence on theta, and so on. It is common in acoustics work, particularly in underwater acoustics, etc., to try to separate the distance dependence from angular dependence. Okay? So when you have an angular dependence, that just shows in some way the radiation shape in different directions. And then the angle, distance dependence really determines the amplitude away from the source. So I'll probably do one example that shows the separation between them. Now, do you have any questions about this, what we have done? Let me just very briefly review what we did, because I don't think I erased anything. I don't remember. Okay. We take the form of the solution. In this case, we reduce the general solution to radiation only and to axisymmetric, meaning n is equal to 0. Okay, so that's given Legendre functions and Hankel functions of the first kind. Coefficients, the way one finds it is through the velocity, the boundary conditions. Well, boundary conditions can be a number of different things. It can be something vibrating here, or the whole thing vibrating, and so on. In order to be able to, well, we wrote the boundary condition right here. So, and we came over here, we said, fine, the coefficients are expressed in terms of um, the coefficients of this velocity distribution. So, and the next thing we did, and you can compute this for any distance, for any kind of configuration. But it is very common to see, okay, I am away from the source. What would be some of the simplifications of the computation? And then we do a far field expansion of the Hankel function, which is, as you can see, 1 over r. As you go away from a source, it's like an intensity, 1 over r squared change. And we find the intensity, we integrate it around the source, that's the power. So these are the steps. These are the steps of calculations. Any questions on this? No? Okay. So if I ask you to do this, can you do it? Yes? Okay. Well, let me ask you then. Okay. Let me see. Do I have a good example? Yes. We have all these. Okay. I think we did in class, but see if you can just start looking at these and starting to calculate radiation from a uniformly vibrating source. What would you do? We did some of this. Don't look at your notes except today's. What would be the power from a sphere that radiates uniformly in and out? How would you calculate it? First, think about what is the question? What is the question? Well, this is engineering now, okay? You're asked to solve something, and you have all the knowledge. First, need to understand the question. What is the question? Do you understand what the question is? No? Okay, let me say, what is the sound pressure? I said power earlier, but let me simplify it. What's the sound pressure from a sphere that vibrates uniformly? Okay. Then what? And then put m equal to 0 and everything. That's an approach, but to be more complete, because some problems are going to get more complicated later, first thing you do is what I have just said to you as the problem, write it in mathematical form. And in this case, what you need in math form is the expression for the velocity. Okay? What is the velocity for that? Just write that, and let's see. You can tell me, and I can write it. Do we have all these? Yeah. Okay, so we have on the surface R equals A, theta phi t. How would we write this? What is this expression?
I think theta will not be here because...
Okay, but what is the right-hand side? The velocity on the surface, graphically, I said something that's vibrating uniformly. That means it's like a balloon that expands and contracts, okay, at a particular amplitude. So particular amplitude is this. What else does it depend on? It depends on time. And what else does it depend on? Phi, does it? It's symmetric. It depends on nothing else. Okay? It depends on nothing else right now. Now, you can make it depend on phi, then it's not axisymmetric, etc. But this is the simplest possible case. And what do you do next is this. Expand it, because you need to find these coefficients, and these coefficients are in terms of u sub m. Okay? So we say fine, here's now uat, because we said it doesn't depend on these, and that is n0. I'm doing this, overdoing it, but this is just to make sure that we follow the steps completely. Um, Pm theta. Okay, and that means U0, P0, U1, P1, and so on. And all of this is that. Now, left-hand side is just some amplitude. These are not necessarily the same, it's a coincidence, but from here, for this equality to hold, these must be all 0. Okay, so now this brings it to exactly what you were saying, so m is equal to 0. And if you substitute m equal to 0 into these expressions, we get exactly what Emrullah suggested a moment ago. And let's do that. Let's see, I don't want to erase everything, but The pressure also is independent of any angular variation. So we end up with this simple form. This would be the pressure from a uniformly expanding source. Now, P sub 0, the zeroth order Legendre function, is equal to 1 because there is no angular dependence, okay? Is equal to 1. And A0, if we remember the relationship, okay, from here we can say A0 is 0, 0. Okay. These are all functions of Ka. And let me just substitute all of these. All right. Now, let's look at asymptotic cases for small values of Ka, such that in this case it's 1/2 really. B0 can be approximated as 1/Ka squared, and L0 is approximated and then no. Very important to remember here for Ka to be very, very small. Okay, M is 0, so it's really less than 1/2. Okay, in this case. And I'll discuss what that means in just a moment. Let me continue with this. Okay, that's the, for a small source, we said Ka very small. In addition, far field. And when somebody says far field, we look at that. What do? You look at the expression, and what do you do in the far field? To calculate the far field, you substitute an approximation for the distance, the Hankel function, okay? And that distance was exponential divided by Kr, okay? And that gives us now we have okay. One last expression here is okay. Write these and let's talk about them for a few minutes. Okay. All right. Just a very quick review. Okay. Radiation from a uniformly expanding sphere. We said, okay, to reduce this, we found out that only the zero order of Legendre function, and of course by implication, Hankel function are involved. And so we have this very simple expression for a simple source for any arbitrary radius. And AM, we find it to be an expression given by this. Again, any arbitrary radius, we haven't made any approximations yet. Now, for this sound pressure expression, now we're saying if the radius of the ball or the sphere is small by definition, okay, then these numbers for B0 and delta 0 can be approximated by these ratios, okay? So fine, we substitute them back here. This expression now for small diameter sources becomes this, small diameter sources. Now, let's say, okay, here's a small diameter source somewhere over there, a small loudspeaker that radiates in all directions. If we are far away from it, how will it sound, okay? We make an approximation of the Hankel function, and Hankel function says sound pressure amplitude will reduce by both frequency and distance, and we make that substitution over here. Now let's read this just a little bit, okay? This one. And this is in the far field. It's for small sources. In fact, if the source is so small that we call it a point source, we can write sound pressure expression as such, and this is called source strength. Okay, what does that mean? Let's just take a quick look. 4 pi a squared is the surface area. Okay, since this is uniform, and u0 is the amplitude of vibration. So it's the volume velocity. Okay, this is the air, the velocity of the air that's being pushed out and contracted. That's why it's called the strength of the source. So, and the sound pressure decreases as you go away from the source in the far field. And point sources are concepts that are used to describe sound sources in acoustics, in noise control, etc. So this is one of those examples. The other thing, if you look at these, is, let me see, we said Ka is very small someplace. Yes, for small values of Ka, okay? When you say Ka is very small, and this is a point source, K is, of course, 2 pi A over lambda. So what that really means is for diameters much smaller compared to the wavelength. And wavelength is what? Long wavelengths correspond to low frequencies. So low frequency, at low frequencies, even physically large object can act like it's a point source. Okay? So and these become important in terms of whether it's a loudspeaker design or you're making noise measurements, estimations of small engines, big engines. So it's always a relative value of size of the object to wavelength, or in this case, frequency that comes from the source. Okay? Okay, let's take a 2-minute break or 5-minute break.